It's nice to be here, giving my first in-person talk since January 2020. So I'm going to talk about joint work with Thomas Orponen, until the last slide at least, more or less. Okay, so this is a diverse audience, so let me start from the beginning. So there is a huge area of research that is concerned with what happens when you project a subset of Euclidean space, which is possibly fractal. And I guess Vesicovic's projection theorem is the first important result in this direction, and I guess this is the second. I mean, chronologically, I'm not talking about level of importance. They are both important. Okay, so Marston's theorem says that if we have a Borel subset of the plane, and let's say that the dimension is at most 1, this is a relevant regime for this talk, then the dimension of the set is preserved under almost every projection. So even though in general projections are not expected to be injective on A, as far as dimension is concerned, a typical, actually, even if it was injective, this wouldn't guarantee that the dimension is preserved. But nevertheless, the projections in a typical direction behave nicely enough that the dimension is preserved. And this almost all is according to Lebesgue measure. So this is important, very important. So this is sort of the beginning of the motivation or the history of the problem. So one can ask whether it's possible to refine this. And in fact, again, this is a very large area, and this has been refined in many different directions, but a very natural direction to try to refine this is, can we make the exceptional set smaller? So can we say that the dimension is preserved, not just for Lebesgue, almost every angle. So P theta A is the orthogonal projection in direction theta. So we can ask, can we say something stronger? Can we say that the dimension is preserved not just for Lebesgue almost every angle, but maybe for every angle outside of a set of angles of small Hausdorff dimension? So any Hausdorff dimension strictly smaller than 1 would be an improvement, a strengthening of saying that this equality holds for Lebesgue almost every angle. So Lebesgue almost every angle means the exceptional angles for which this could fail have 0 Lebesgue measure, but saying that the exceptional set has dimension less than some number, which is less than 1, would be a stronger statement. And in 1968, Kaufman did 2 things in a 2-page paper. He provided an improvement in the direction that I was suggesting in the previous slide, and also introduced a much simpler proof that was the first instance of what became the potential theoretic method, which became a very powerful and method to prove many things in fractal geometry later on. Okay, so there are several ways to state the theorem. And again, there are also results that say what happens when the dimension of A, the set in the plane, is bigger than 1. But in today's talk, I'm going to assume that it's at most 1. Okay, so here we have 2 parameters, S and T. And throughout the talk, T will be the dimension of the set we are projecting, and S will be the dimension of the set of projections. So we have a set A in the plane that has dimension T, and we have a set of directions that has dimension S. So the directions we can parameterize by elements of the circle, although this is a 2-to-1 identification, but this is not important because we are only going to consider dimension. This 2-to-1 map doesn't affect dimension. Okay, so Kaufman proved that if T is bigger than S, so the set we are projecting has dimension larger than the set of directions that we are considering, then the dimension of the projection is at least the dimension of the set of directions outside of a set of directions, which is, well, at most that number. So S stands for the dimension of the set of exceptional set of directions. So if we have a set of dimension, for example, 1, and we consider a set of directions of dimension 3/4, then there will be some point there such that the projection of the set of dimension 1 has dimension at least 3/4. So this is what the theorem is saying. But also, if we have a set of dimension 1/2, and we project it via a set of dimension 1/2 minus epsilon for any epsilon, there will be some point there for which the projection has dimension 1/2 minus epsilon. And that epsilon is arbitrary. So a corollary of that, that involves only 1 parameter, is that if we have a Borel set of dimension at most 1, then the dimension of the set of angles for which the dimension drops from the dimension of the set has at most the dimension of A. The dimension of the set of angles for which the dimension drops from the dimension of the set upstairs is at most the dimension of the set upstairs. And if the dimension of the set upstairs is less than 1, this is stronger than mass transprojection theorem. It says that the set of exceptional directions for which the dimension could possibly drop not only has Lebesgue measure 0, but in fact has dimension at most the dimension of A. So the smaller the dimension of A, the bigger the strengthening over mass transprojection theorem that this estimate provides. And there are examples showing that this is sharp. So there could be a set sharp in the sense that for every S, or for every T, I guess, there is a set of dimension T for which this set here, oh, sorry. Well, you can see, so it doesn't matter. But anyway, this set here actually has dimension T. In particular, if the dimension of A is 1, one cannot really improve mass transprojection theorem, at least using Hausdorff dimension. So the set of projections for which the dimension drop has 0 Lebesgue measure, but if A has dimension 1, then the set of bad directions could also have dimension 1. And it's a subset of the circle. So dimension 1 means that at least from the point of view of dimension, it could be as large as possible. Okay, so right. So here is Kaufman's theorem again, stated in a slightly different way. So we have a set of dimension T, and we have a parameter S, which is at most T. Then the dimension of the projection drops below S for a set of directions of dimension at most S. And as I said, yeah, so this is a refinement of Marston's theorem, but also Kaufman provided a simpler proof. And actually, I'm going to show you the proof in the next couple of slides. But something that is not very satisfying is that T doesn't show up. So of course, T has to be bigger than S, because the fact that this is sharp when T is equal to S. Okay, so T cannot possibly be smaller than S, because then the dimension of, if T was less than S, if you put a T here, this is nonsense, because orthogonal projections do not increase dimension. If the dimension is T upstairs, it is at most T downstairs. So T has to be at least S. But other than that, there is no T in the statement. So T has to be larger than S, but in fact, one could say that T is S and be done with it, because the theorem doesn't provide any additional information if T is much bigger than S somehow. So in this sense, it's not very satisfying. And that's sort of the motivation for, well, several of the things I'm going to talk about later. Okay, so again, some of you are familiar with this, but some of you maybe are not. So let me very quickly show you that this is actually, I mean, once you know how to do it, the proof is very short. So recall that the Riesz S energy of a measure is the integral of 1 divided by the distance between x and y to the s, the mu x, the mu y. And the version of Frostman's lemma says that there is a very close connection between the critical parameter s for measures supported on a set and the dimension of the set. So basically, they are equal. These two things are equal, in the sense that if we can put a measure on a set A for which the S energy is finite, then the Hausdorff dimension of A is at least S. And conversely, if the dimension of A is S plus epsilon, then one can find a measure on A that has finite S energy. So again, the Hausdorff dimension of A is the critical S for which we can find measures that live on A that have finite S energy. Okay, so once we know that, then the point is that we can look at all of the projections of A using just one single integral. And then once we have an integral, one does Tubini, and basically that's the proof. Okay, so here are a bit more details. So suppose that we have a set of dimension bigger than S. And because the dimension is bigger than S on Frostman's lemma, there is a measure on A with finite S energy. And we have already used that T is bigger than S. Okay, so the way I stated Kaufman's theorem in the previous slide, T could be equal to S. But now, okay, so there are epsilons flying around that can tend to 0, depending on whether one puts strict or non-strict inequalities. But here I want it to be bigger than S. And the only way I'm using that is to say that there is a measure on A that has finite S energy. So if T is much bigger than S, this makes no difference, because this is what the proof uses, and it's sort of very hard to sort of exploit the fact that T is bigger, much bigger than S. Okay, so this is something I'm going to comment on later, because that's the point of the result with Thomas. Okay, so suppose that the claim in Kaufman's theorem is not true, and that means that the dimension drops below S on a set of dimension bigger than S. And then we put a measure on the set of exceptions, on this very large set of exceptions, larger than is actually possible. So we want to reach a contradiction. Okay, so we are assuming that the set of directions where the dimension drops too much is too big. So we can put a Frostman measure there. And then we look at this integral. And the point is that if we can prove that this integral is finite, we are done. So what is this integral? We have mu, which is a measure that lives on A, which is upstairs in R2. So we can project the measure orthogonally with direction theta. So this measure lives on the projection of A. So if this is finite, if the integrand is finite, by the other direction of Frostman's lemma, this measure lives on a set of dimension at least S. But this measure lives on the projection of A, and the integral is with respect to rho. So this will be a contradiction because rho lives on sets whose projection has dimension less than S. And if this is finite, and it is finite, then by Frostman's lemma, actually the dimension of this is at least S for almost every rho, almost every theta, in particular for one theta, and that is a contradiction. So this is why the whole thing is reduced to just estimating one integral. And okay, so estimating this integral is not difficult. So first of all, by definition, we are just taking mu and pushing it down via the projection. That means that we can apply the projection inside and integrate with respect to mu. And once we do that, we just apply Fubini, integrate with respect to rho first. And then there is a short calculation using the fact that rho is a Frostman measure that gives that this is bounded by a constant times the distance from x to y to the minus s. And this is the S energy. And by assumption, it is finite. So that's all. So that's the proof. OK, so if you have any questions, by the way, you can stop me at any time. OK, so so now we do have a parameter t, which somehow doesn't really show up in Kaufman's theorem, but that's just an artifact of the proof. So it does show. So in real life, the larger the dimension of the set one is projecting, the better things should behave. So then we can introduce a function gamma of st, which is sort of the best you can hope for, that in the sense that it's the same number that works for every set A, just in terms of the dimensions of the set upstairs and the dimension of the set of directions. So gamma of st is the largest number, such that for every Borel set in the plane with dimension t, the dimension of the projection doesn't drop below this number outside of a set of directions of dimension s. Okay, and I guess this is equivalent to what I wrote. So again, we have a set of dimension t, we have a set of directions of dimension s. If we can guarantee that some of the projections, so at least one projection of the set of dimension t, where we take the direction from the given set of dimension s, if we can guarantee that one of those projections will have dimension gamma of st, that's a lower bound for gamma of st. And the question is, what is the real value of gamma of st? Okay, and Kaufman theorem gives such a bound. It says that gamma of st is at least the minimum between s and t. So when t is at least s, well, it is s. This is exactly what Kaufman's theorem says. And if t is less than s, we replace s by t. And it's again Kaufman's theorem. Okay, so there is a conjecture which is very, very hard. So if you are not familiar with this area, okay, you will not see why this is very hard, but believe me, it is very, very hard. So the conjecture is that this is 2s minus t. There are several motivations for the conjecture. One is that it holds at the endpoints. So when s is t over 2, this is 0. And it is known that when s is t over 2, this is 0. And it's not 0 for any other. So this is the right threshold for being 0. And when s is equal to t, we get t, and this is Kaufman's theorem. Okay, so it's true at the endpoints, and it has to be something, so why not linear? So we have a function of two parameters. We know what it is. So if we fixed t, we know that at t over 2 and at t, it takes the values of this function. So if the function is linear in S, it has to be this one. And it has to be some function, so why not linear? Okay, that's maybe not a very good motivation. So there is a better motivation coming from discrete incidence geometry. Okay, so if instead of projecting a fractal, you project a finite set of endpoints, then this is the right threshold if you formulate the problem in the correct way. So maybe that's a better motivation, but anyway, so this conjecture is completely beyond reach at the moment, but some things are known, some interesting and highly non-trivial things are known. So the first sort of new result in this area after Kaufman's theorem was a result of Kenneth Falconer from the mid-80s. And actually, okay, so this was stated in this way in a later paper of Perez and Schlack, but I would say that the proof was at least implicit. Okay, so Falconer proved something else, but closer related to this, I would say. Okay, so it says that, so this basically, so this is better than Kaufman if t is bigger than 1, as you can see, because if t is bigger than 1, this is bigger than s. And Kaufman gives s. So suppose that t is at least s. This is really the interesting case. By the way, if t is at most s, then Kaufman is sharp. So that's the answer. So so this is the regime that is interesting. S between t over 2 and t. If s is less than t over 2 or t is less than s, then everything is understood. Okay.
Is it possible that S and gamma of S be split in that offset of S? No, the higher one.
Here?
One higher. Yeah. Is it possible that that should be S and then S on the right should be gamma of ST?
This is gamma of st and this is s. No. Okay, so maybe it should be flipped. Okay.
If S is t over 2, then this would be saying that the dimension of the set of projection. If you look at the set with Hausdorff projection.
Okay. Did I write it the wrong way around everywhere then? Okay. Right. So okay. So if S is t over 2, yeah, I want to get half the dimension here. Right. Yeah. Thank you. Yeah. Thank you for noticing this. Yeah, you're right. So okay. So this is bad because now nothing will make sense. But yeah, this should be S and this should be gamma of ST. So the question is then. No. Wait. Oh, right. Okay. Yeah. Okay. So yeah. So you're right. Yeah. So this should be flipped around, which is not very good because now at some places it should be flipped around. I guess at some places it doesn't have to be flipped around. So yeah, this is not good, but right. So I guess.
Excuse me, Pablo, can you tell us what was wrong? Because it wasn't clear from outside. We cannot see what you are pointing.
Oh. Okay. Right. So yeah. So what Josh pointed out is that, for example, if the set of directions has positive dimension, then the dimension of the projection is at least t over 2. Right. So what this is saying is that with this definition of gamma, what this is saying is that gamma of st, if s is positive, yeah, so it is flipped around. So basically, this should be s and this should be gamma of st. Sorry about that. But basically, it should be the inverse function. So for a given t, I guess gamma to the -1. This is gamma to the -1. Maybe that's the easiest way to fix it.
Thank you.
Sorry about that. Okay. Yeah, I guess this is still with the flipped gamma. So at least, basically, you only have to change here. This should be S and this should be gamma of ST. Okay. So yeah, so Falconer proved, or Falconer, and then in this precise form, Perez and Schlack proved that if t is bigger than 1, which is somehow a case that I've been forbidden until now, but actually now it makes sense. So if t is bigger than 1, but s is smaller than, so if f plus t is smaller than 2, this, well, even if it is 2, this is better than Kaufman because t minus 1 is bigger than 1. And then, yeah, so there is a, so is this still consistent with the thing being flipped, or am I back to? Okay, so No, it's okay. It's still consistent with being flipped. So we only have to fix one thing. Okay, and then, right. So what this says is that if we have a set of directions that has positive dimension, but it could be very small. So suppose that T is 1, for example. This is maybe the most interesting case. T is 1 and S is very small, a positive but very small number. Then this is saying that even though S has very small dimension, still if we have a family of S-dimensional directions, the dimension of the projection will be a little bit bigger than 1/2. Well, according to Kaufman, only tells you that it will be at least S, and S is 0.0001. So this tells you that if you project a set of dimension 1 through a set of directions of dimension 0.0001, the dimension is going to be 1/2 plus some epsilon that depends on 0.0001. And without the epsilon, well, this is folklore. It was explicitly written out by Orponen, but I think Oberlin's paper is after Buchan's paper, and this is a stronger and many orders of magnitude more difficult statement. So this epsilon is extremely important. So it's very hard to, so it makes a world of difference having this epsilon versus not having the epsilon. Without the epsilon, this is relatively easy. With the epsilon, is a major result. Okay, so this is better than Kaufman if S is at most T/2 plus some little epsilon that is not the same epsilon, but depends on this epsilon, right? Because Kaufman gives S here. So when this is S, when this is bigger than S, this is better than Kaufman. Okay, so we have these two results, which are each of them significant for many reasons. And they each improve upon Kaufman on sort of different regimes, but still there is a very large region in the middle where Kaufman remained the best bound. Well, basically, if S is at least a little bit bigger than T/2 and strictly smaller than T, Kaufman's bound remained the best. And then with Thomas, we improved Kaufman by some very, very small epsilon. So this is our first main result. So for every S positive strictly less than T, there is an epsilon such that gamma of ST is bigger than S. So this says, for example, that, so let me translate this, especially because the definition was wrong. So let me translate this into words. This says that if we have a set of dimension 1 in the plane, and we have a set of directions of dimension 3/4, we can find some direction in this set for which the projection has dimension at least 3/4 plus epsilon. And yeah, Kaufman gives 3/4, and this was the best known. So 3/4 was still the best known bound for this particular choice of parameters. Okay, so now this epsilon depends on 1 3/4 and is very small, but it is positive. Okay, so let me switch to the next topic, which is Furstenberg sets. So what is a Furstenberg set? It's sort of a fractal analog of a Kakeya set. And I'm going to, everything today is in the plane because the plane is already difficult enough. So a subset of the plane, I mentioned this because the Kakeya sets are completely understood in the plane, but Furstenberg sets are not. Okay, so a set in the plane is an S Furstenberg set if for every direction there is a line pointing in that direction such that the set intersects that line in dimension at least S. So if S is 1, this is almost a Kakeya set. But okay, the interesting thing is when S is not 1, when S is smaller than 1. Okay, and one can generalize this instead of requiring a line in every direction intersecting the set in dimension at least S, one can have some family of lines. So lines are parameterized by, so lines in the plane are a manifold, Grassmannian manifold of dimension 2. So we can speak of Hausdorff dimension of a set of lines. And an ST Furstenberg set is a set for which there is a family of lines of dimension T, not necessarily pointing in different directions, such that the set intersects all lines from the set of lines in dimension at least S. So in particular, the classical Furstenberg set is an S1 Furstenberg set, because if you have a line in every direction, you have at least a one-dimensional family of lines. Okay, so a Kakeya set is a 1 Furstenberg set, and a classical S Furstenberg set is an S1 Furstenberg set, as I mentioned. Okay, so a question that was introduced, well, it was not impressed, introduced by Furstenberg, and then it was written down by Wolff, is how small can an S Furstenberg set? And Wolff proved, although he says that at least the upper bound, sorry, the lower bound, Wolff says that it was probably known to other people. Okay, so he proved a lower and an upper bound, and the upper bound is what is conjectured to be the truth. But okay, so I told you that there was this conjecture about the real value of gamma of ST for projections, and I told you this is very hard. Well, this is even harder. So it's much harder, or at least, well, I don't know if much harder, but at least as hard, and probably harder than something very hard, so also very hard. Okay, on the other hand, the lower bound, okay, there are two lower bounds. So this is better when S is between 1/2 and 1, and this is better when S is less than 1/2. Yeah, these are not so hard to prove. And there are corresponding bounds when you have this more general setting where you have a family of lines. So this problem was first introduced by my Argentinian friends, Ursula Molten and Ezequiel Rela. Anyway, so there are some corresponding bounds. These bounds correspond to the bounds proved by Wolff in the case of a classical Furstenberg set. And there is a very nice recent result of Dabrowski, Thomas, Orponen, and Villa that is better than this when T is strictly larger than 1. So you can look at their paper. I'm not going to mention it now. Okay, and now I would like to explain that the Furstenberg set problem is harder than the projection problem. So I told you it's at least as hard, and now I'm going to explain why. So, so a set of, in R2, I will use it to parameterize a family of lines in the sort of the obvious way. So the point AB corresponds to the line Y equals AX plus B. Okay, so this doesn't include vertical lines, but this is irrelevant for anything I'm saying. So from now on, I basically will identify a subset of the plane with a subset of all possible lines, where again I parameterize the lines in the obvious way. Okay, and suppose we have a subset of the unit interval, a subset of R, but let's say the unit interval of dimension S, and then I can construct the following Furstenberg set. But this is a very, very special class of Furstenberg sets. So this is by no means the most general possible Furstenberg set. On the opposite, it has an extremely rigid structure. Basically, it has the property that on every line we have the same set. So a Furstenberg set is a set that intersects some lines in dimension at least S, but the actual intersection could be totally different. In this case, the intersection in some sense is always the same. Okay, so it's a set of points X, AX plus B, where X is taken from the set of dimension S, and AB is taken from this point, therefore, sorry, from this set A that parameterizes the lines. Okay, so it is a Furstenberg set, right? Because for every line, so it is a generalized Furstenberg set, because for every line parameterized by A, well, we have a copy of E, and E has dimension S. So this is an ST Furstenberg set, but it is a very special ST Furstenberg set. And for this very special Furstenberg set, we have the following easy identity. So if you look at the vertical slices, so I intersect F with the points whose X coordinate is some given X0. Well, first of all, X0 has to be in E, otherwise this is empty, by the way I define the set. And if X is in E, if X0, sorry, is in E, well, then the slice, so the vertical slice is this, and X0 is fixed, but the point AB comes from the family of lines. So for fixed X0, AX0 plus B is a projection with some direction, which is something like the arctan of X0 of the point AB. So the vertical slices of this very special Furstenberg set are essentially orthogonal projections up to reparametrization of the points AB that parameterize the set of lines. So again, for this very special sort of product Furstenberg sets, the vertical slices are either empty if the point is not in E, or if the point is in E, they are given by an orthogonal projection parameterized by E of the set of lines, or the set of parameters for the set of lines. And this suggests that at least morally, if there was, which there isn't, but let's assume for a minute that there is a sort of natural Fubini relationship for Hausdorff dimension, then the dimension of F should be the dimension of E, so the dimension of the projection to the first coordinate, plus the dimension of a typical slice. Again, this is not true, but morally, this is what one expects. So we have a subset of R2 of dimension T. So now you see why I chose these letters for the parameters. So we have a set A of dimension T. And if we believe this heuristic identity, the dimension of the Furstenberg set is a dimension of E, which is S, it is fixed, plus the dimension of the projection, when I use E as a set of directions, which has dimension S. So if we understand the projection problem, we should understand, morally at least, the dimension of Furstenberg sets, but for this very, very special class of Furstenberg sets, not for other Furstenberg sets. So for this reason, okay, so this is again the definition and the moral equality. Okay, actually, this is the moral equality. One inequality is actually true, the other is not true, but it is true if you discretize the problem at the fixed scale delta. So it's close enough to being true. So this moral equality is close enough to being true that morally and in practice, the Furstenberg set problem is at least as hard and often harder than the projection problem. The Furstenberg set problem for this very special class of Furstenberg sets is essentially equivalent to the projection problem. But there are many Furstenberg sets that do not have this projection structure. Okay, so so it turns out that S2S Furstenberg sets are special. So in particular, one half classical Furstenberg sets are special. In that case, 2S is 1. So we're in the realm of classical Furstenberg sets. Okay, so in this case, so recall that for any S and T, if for any S less than T, less or equal than T, gamma of ST is at least 2S. Okay, this can be improved by an epsilon for S2S Furstenberg sets. And this was first proved for classical Furstenberg sets by Bourgain, I guess, relying on well, I would say Katz, Tao, and Bourgain. So Bourgain, but relying on previous work of Katz and Tao. And then for general S, it was proved by Cornelia Hera, myself, and Alexia Iavicoli. And then recently, Daniel Di Benedetto and Josh made this epsilon explicit. So here is an epsilon that works. Okay, so so this is not easy. I mean, you can imagine by just that it took two Fields medalists and Ned Katz, who is also very smart, to get this for classical Furstenberg sets. And then what we did, and well, Di Benedetto and Josh did. Okay, it's not trivial, but it's building on the ideas of Katz, Tao, and Bourgain. So yeah, so this is not easy, but on the other hand, it is crucial that T is 2S. Because when T is 2S, so this is non-trivial to do, but it turns out that if gamma of S2S is very, very close to 2S, then the Furstenberg set does have to look like a product Furstenberg set, one of the very special Furstenberg sets from the previous slides. So this is morally what's going on. And once you have a product Furstenberg set, this is equivalent to the projection problem. And in the projection problem, we have Bourgain's projection theorem that gives you an epsilon gain. So that's sort of the origin of this epsilon gain here. Okay, so this is difficult, but on the other hand, it strongly uses that T is 2S. So again, gamma of SS is 2S. And gamma of S2S is at least 2S plus epsilon. So what happens between S and 2S? So do we really need to go all the way up to 2S to get some improvement over the bound, sort of the easy bound 2S? And it turns out that we don't. So this is our next main result. So with Thomas, we prove that, again, we have 0 less than S, less than T. Well, T could be actually a bit bigger than 1. This is still interesting when T is a bit bigger than 1. But okay, nevertheless, then we can get an epsilon improvement over this sort of easy bound 2S. And this is as soon as t is bigger than s. So we don't have to go all the way to 2s. Okay, so yeah, so these problems, so they are not isolated problems. They have many connections, and in the discrete setting, so all these problems are in some sense continuous version of incidence problem in discrete geometry. And in discrete geometry, there are still many open problems, but at the same time, some of the connections become much more transparent. But in this sort of fractal setting, these connections were first studied in detail by Katz and Tao. Okay, anyway, so there are well-known connections to the Kakeya problem, to the Falconer distance set problem, to the discretized sum product problem, among many others. And these are three major problems in geometric measure theory and harmonic analysis. So these are not isolated topics. But actually, I've stated everything in terms of Hausdorff dimension, but the Hausdorff dimension versions that I stated, they are not really related to each other, or so maybe to be more precise, if you want to relate them to each other, you have to pass to discretized versions. And by discretized, I mean state versions of all of these theorems or questions at a finite scale delta. And then you can find connections, which are mostly non-trivial, but okay, there are many well-known connections between all of these problems. Okay, so I want to state the discretized version of our theorem, because this is the version that is actually connected to all of these other problems, so the discretized version. Okay, so there is a notion of delta S set or delta S C. Maybe you can forget about the C if you haven't seen this before. So a delta S set is a set that at scale delta behaves like a set of dimension S. So this is the intuition to keep in mind. And okay, so the bar with delta means the smallest number of delta balls required to cover a set. And the condition is sort of like a Frostman condition, but where instead of having a measure, we look at the delta covering number of the set intersecting with the ball. And I didn't write it here, but R should be at least delta. Well, I guess it doesn't matter, actually. Yeah, actually, it doesn't matter. It doesn't have to be. Okay. Okay, so again, if you haven't seen this before, just imagine that this means that at scale delta, the set X looks like a set of dimension S. Okay, so here is our discretized estimate. Okay, so it's a bit long to parse, but essentially it is saying that if we have something that looks like a Furstenberg set at scale delta, then the delta covering number is at least delta to the minus 2s minus epsilon. So we have a sort of this epsilon gain in the dimension. Okay, so we have the same parameters as before. There is an epsilon as before. It's basically the same epsilon. And it says that if we have a set of lines, so A parameterizes the set of lines, and it's a delta T set, so it looks like a set of dimension T at scale delta. And then we have F, so F stands for our Furstenberg set. And basically what happens here is that we don't know what happens on a line, but we know what happens in the delta neighborhood of a line. So we look at the points in F, which are delta close to the line parameterized by AB. So this is essentially looking at the intersection of F with the tube center around the line parameterized by AB and with delta. Then this should be S dimensional at scale delta. Okay, and then we have a lower bound that corresponds to dimension 2s plus epsilon for the size of F delta. So at the discrete scale delta, this is essentially saying that the discretized ST Furstenberg set has dimension 2s plus epsilon. Okay, and this is really the main result from which we can get as corollaries that take some work, but are sort of standard, the Hausdorff dimension versions that I stated before. And this is in itself a sort of an active and difficult area. So studying incidences between tubes and points, or incidences, but with an error allowance of size roughly delta. Okay, in the last 6 minutes, let me tell you a little bit about some of the things that go into the proof. And the starting point is an earlier result of Thomas, who proved that the packing dimension of an S Furstenberg set, a classical S Furstenberg set, is at least 2s plus some epsilon. If you don't know what packing dimension is, you can think of upper Minkowski dimension, upper box dimension, or you can look at the discussion that follows. So again, Thomas deduced these results from a discretized statement at scale delta. But there were 3 caveats. One caveat is that Thomas needed sort of a weak regularity assumption on the set A. So A is a set of lines, set of that parameterizes a set of lines. So basically, Thomas considered 2 scales, delta and square root of delta. And he needed to assume that at scale square root of delta, the set A is not too large. So it also looks t-dimensional scale delta square root of delta. So a set can look t-dimensional at one scale, but it can look like a bigger dimensional set at the coarser scale. This can happen, and this is what Thomas needed to avoid in order to get the estimate. And then under this assumption, he got again, so this E should be F. This E should be F, so that this discretized Furstenberg set has an epsilon gain at either scale delta or scale square root of delta. And also, this is for classical Furstenberg sets. So essentially with T equals 1. Okay, so in order to get our theorem, we need to replace T equals 1 by any T. And this part is not so hard. So it's basically looking at what Thomas did. And okay, so the case of general G requires some changes, but not too many changes. Then there is the second problem is that we have this dichotomy. We want to have a gain at scale just delta, not either delta or square root of delta. Well, it turns out that if one still assumes the regularity, one can get rid of the scale square root of delta. The dichotomy is not needed. If we have this assumption, then we have a gain at scale delta. And this is also not very hard. So the remaining hurdle is to remove this assumption. And that is the hard part. So this, in general, does not need to hold. And this is where we have to do something. Oh, by the way, so Orponen's proof is a very highly non-trivial application of Burgan's projection theorem. So at the end of the day, this epsilon comes from the epsilon in Burgan's projection theorem that I told you is very important. Okay, so I have 3 minutes to try to explain something that I cannot explain in 3 minutes, but I'll try. So, so if the set is regular in the sense that at scale square root of delta, it looks t-dimensional as well, we are good. But in general, the set doesn't have to satisfy this. So the trick is to, given the set A, find scales depending on the set A, so the composition of the scales, with the property that if we look at the set at one of these scales, going down to the next scale, okay, and the way to do this is to intersect the set with a ball of radius the scale and magnify it so that sort of renormalize it back to the unit ball or something like this. And then we look at the next scale, which means that because we have renormalized by this, then we have to look at this quotient as the new scale. Then at each scale, one of 2 things happen. Either the set is regular in the sense that allows us to extract an epsilon gain, or it is not. And it is regular if, okay, so at each scale, the set has sort of a dimension associated to it, which I call Tj. And this can depend on the scale. But at some scales, the set looks like Tj regular, with Tj is at least T. And the other scales, we don't know, but at least it looks like an Sj dimensional set, where Sj is between S and T. And actually, there is a very small set of scales where we don't know what happens, but that is very small, so we can ignore it. But the important thing is that the first alternative holds for positively many scales. So we do see that in this multi-scale decomposition, at some scales, the set looks regular, and at those scales, we can use, well, the epsilon gain for regular sets to say something about the intersection of the set, the incidences of the intersection of a set with a small ball. Okay, and then we have to put all of the scales together. And this is what takes most of the space of the paper, which is quite long. So putting all of the scales together. So this is another sort of new thing in the paper, which hopefully will be useful for some other problems as well. And again, because there is an epsilon gain at positively many scales, this gives some other epsilon gain overall when we combine all of the scales. Okay, and I have 30 seconds to give, well, to mention very briefly another result that I obtained together with Han Wang that strongly uses the result, the discretized result that I proved together with Thomas. So recall Falconer distance conjecture. So it's a very famous conjecture that says that if we have a Borel subset of Rd of dimension, okay, so there are several versions. This is one version. We have a Borel set of Rd of dimension at least d over 2. Then the set of distances spanned by pairs of points in the set has full dimension 1. And together with Wuhan-Wang, we proved several things. In particular, we proved that the conjecture is true for alpha's regular sets and more general for sets of equal Hausdorff packing dimension, which is a class that strictly contains alpha's regular sets. Okay, and there are many things that go into this theorem, but sort of the starting point and the key tool is the epsilon gate for discretized Furstenberg sets. So we are able to bootstrap or self-improve the epsilon all the way up to the conjecture, at least for this class of sets. And this is something that happens in other contexts as well. So even though the epsilon is very, very small, there are some situations where it's possible to self-improve it to get some macroscopic gain, not just an epsilon. Okay, that is all. Thank you very much.